Section 5.6, inverse of a function. This is the final section of Chapter 5. I'm going to start with an example. Let f of x equal 2x plus 3. And the first task is to solve y equals f of x for x. What we're going to do first is we're going to replace f of x with y. So we're going to have y equals 2x plus 3, and then we're going to solve for x, and so we're going to get x by itself. So the first thing we need to do is to subtract the 3. So we're going to have y minus 3 is equal to 2x, and then we have one last step. We just need to divide both sides by 2. So then our final answer here for part number 1 is going to be x equals, we're going to have y minus 3, and then we've divided that whole thing by 2. Okay, so step number 2, find the input when the output is -7. Okay, so the input, so I'm going to do that in blue. The input, that's x. Okay, the output, that's going to be y. And regardless of where it's at, input usually stands for x, output is usually y. Okay, so it tells us the output is -7, so we need to figure out what x is. Okay, so x equals -7 minus 3 all over 2. -7 minus 3 is -10. Divided by positive 2, that gives us -5. That's going to be the first part of your assignment, where it's going to have you solve for the opposite variable, or replace f of x with y, and then solve for the input, or the independent variable. And then it will give you the output, and you need to go find the input. Okay, so the meat and potatoes of this section centers on the idea of inverse functions. And inverse functions are functions that undo each other. Okay, in inverse functions, the x's and y's are reversed, or they're switched. Okay, so if I gave you f of x equals 2x plus 3, and then I gave you g of x equals x minus 3 over 2, what you would find, if you did an xy table for this one, did -2, -1, 0, 1, and 2, your y values here would be -1, +1, 3, 5, and 7. Now, if you did an xy table for this one, xy, what you would find is that the ordered pairs, -1, 1, 3, 5, 7, these are actually switched. -2, -1, 0, 1, and 2. Okay, notice that in inverse functions, the x's and y's get flipped over. Okay, they're still in the same order, x comma y, but notice that these x values in the first function are now the y values of the second, and vice versa. Okay, the x values of the second are actually the y values of the first. Okay, and we're going to find that in any pair of inverse functions. Okay, just visually what we're looking at, the graphs of inverse functions are reflections over the line y equals x. So I've got this nice little picture here from Desmos. The blue line here, this is the line y equals x, and I've got that over here. The blue line is y equals x. So what we should see is that the red line, the f of x, and the green line, g of x, should be reflections over that blue line. And you can see that they are. So pick a point, go straight to the line, and those are the same distance away. It's a nice reflection. With lines, it could be sometimes a little difficult to see. We'll be working with more complex functions in this section. For example, here I've got 2 times the cube root of x minus 4 plus 1, and x minus 1 over 2 cubed plus 4. You can see the reflection happening. Here's the original one in red. Here's the reflected one, or the inverse function, in green, and you can see that it's a nice reflection over that line y equals x. So that's a little more visual example of what's actually happening here. We're flipping the x's and y's. We're reflecting the original over the line y equals x. Don't feel like you have to write this example down. I'm just showing you visually what's happening. If you want to use Desmos to kind of check yourself, feel free. It's a great resource. It's a free resource. You can use your computer. Desmos also has an app that you can do the same thing on your phone, or if you have a tablet, you can do that as well. Okay, so let's actually move on and figure out how to actually find inverse functions. The process is pretty simple. We're going to switch x and y, and then resolve for y. That's all there is to it. Okay, so for a couple of examples here, find the inverse of the function, then graph the function and its inverse. Okay, so to start with, let's find the inverse of number 1. The first thing we need to do is we need to replace f of x with y. So we're going to go y equals 2x. We haven't switched anything yet. That's the next step. Okay, so step number 1, replace f of x with y. Replace the function notation with y. and now we'll switch x and y. So x equals 2y, and then it says resolve for y. I'll do that in purple. This is an easy one. Only got to do one step. Divide both sides by 2. Y equals x over 2. I'm actually going to pass on the graphing part. This is going to be, I would recommend using Desmos for this. Okay, if you're asked to graph, go ahead and just check it on Desmos. I'm not really checking to see if you can actually graph a function. I'm hoping by now, this far into Algebra 2, graphing something is really second nature. It's something that I don't need to actually check over. What I'm concerned with is, can you actually find the inverse? Go from the original and find the inverse, okay? What you should see, though, if you use your graphing calculator or Desmos, this line and this line are the reflections over the line y equals x. It would look something like this. Obviously, the first example would look more like this one with the lines, but it's the same idea nonetheless. Whoops, too far. Okay, so number 2, f of x equals 1/3 x minus 2. We're going to switch x and y, but before we do that, we need to bring in a y, so it's going to be y equals 1/3 x minus 2. And then we need to actually go ahead and switch x and y, so it's going to be x equals 1/3 y minus 2. Now we're going to resolve for y, get y by itself. Okay, first thing we need to do is add 2, so we're going to have x plus 2 equals 1/3 y. And then we need to get rid of that 1/3. To get rid of 1/3, we have two options. We can either divide by 1/3, but dividing by a fraction is the same thing as multiplying by its reciprocal. So we'll multiply both sides by 3. The left side of this we can actually distribute here, okay? The 1/3 and the 3 cancel out, so we're going to have y equals. Basically, all I'm doing in this line is I'm switching this side of the expression or equation and this side, just taking this over to here and this over this way. Okay, so the order doesn't have to change, or it's not going to change. Okay, I'm just reorganizing how I write this, because usually when we talk equations, it's y equals something. Okay, so the 1/3 and the 3 cancel out. 3 times x is 3x. 3 times 2 is 6. 3x plus 6. And again, you can check that on Desmos or your graphing calculator to verify that that is in fact the case. So those two examples are examples of linear functions and their inverses. What about nonlinear functions? Okay, so inverses of nonlinear functions. So now we're talking parabolas or absolute value or quadratics or cubics or quartics or square root or anything like that. Basically, the majority of the posters at the front of the classroom, but now excluding linear. Okay, so some inverses are not functions. Okay, so if we think about the function y equals x squared, when we switch x and y, we get x equals y squared. Now this should look familiar. If we remember the section on focus and directrix, so y equals x squared, I'll do that in black. That looks something like this. Okay, but if we start our parabola with x equals y squared, what that does is makes it sideways. Okay, so this is x equals y squared. The black one is y equals x squared. Okay, so now if we remember our rules for functions, the vertical line test, this would not pass the vertical line test. It crosses the same x value more than one time. So how do we get around this? How do we find the inverse of a nonlinear function? Sometimes we're going to have to restrict the domain of the original function. If, for example, I wanted to make this have an inverse, or make it so that the reflection over that line y equals x. So if I drew that line, you can see the reflection there. Okay, if I wanted this to actually be a function, I would have to basically erase this, and if I erase that, well, then I have to erase this part of the parabola. Okay, and then you have the reflection, and the inverse, the purple part, is in fact a function now. So let's just jump around. Let's just jump right into it, okay? So find the inverse of the function, then graph the function and its inverse. I'm actually going to do this graphing part by hand so we can actually see what it is we're looking at. So number 1, we got f of x equals negative x squared, and the domain is limited to x is less than or equal to 0. For now, we're going to leave this part on hold, okay? We're not even going to worry about it when it comes time to actually find the inverse, okay? So the first step, we need to bring in y. So we're going to have, let me get rid of all that. Y equals negative x squared. So we got to bring in y. Now we're going to go ahead and switch x and y. So x equals negative y squared. Okay. Now we're just in the matter of resolving for y. Okay, so let's get rid of the negative. So divide by -1 because the -1 is not part of the base. Okay, so we're going to have negative x equals y squared. And then we just have one more step. We need to square root both sides. Okay, so we're going to have y equals, again, I'm just flipping the equation over. Remember, when we're solving with an even root, in this case a square root, we'd still need plus or minus, and then it's going to be the square root of negative x. Okay, so there is our inverse. Y equals plus or minus the square root of negative x. What we're going to end up doing is we're going to end up choosing one of these two. It's not going to be both. It's going to be one or the other. It's either going to be positive square root of negative x, or it's going to be the negative square root of negative x. Let's try to figure out which one it's going to be. And how we're going to do that is actually using this domain restriction. Okay, I just want to see how much room I've got. I got plenty. Okay, so when we go and graph this, okay, I'm going to draw a scale 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so when we graph this, I'm looking at the original equation, f of x equals negative x squared. Okay, so that it would be 0, 0, -1, -1, 2, -4, and I'm out of room. And then I got 1, -1, and 2, -4. So my function, as is, looks like this. Okay, now, the domain, the restriction says x is less than or equal to 0. So less than or equal to 0 is from here, the origin, all the way this way. So what we're going to end up doing is we're not going to need the right side of this graph. Okay? Now, when we graph this, if you graph this in your calculator, if you did, like y1 equals square root of negative x, and then y2 equals negative square root of negative x, what you would get is something that looks like this. Now, I'll actually do the second one in green so we can see the difference, and then we can really decide which one is which. So if you do positive square root of negative x, what you're going to get is something that looks like this. Okay, if you do the negative square root of negative x, you're going to get something that looks like this. Question then becomes, which of the two is the actual reflection over that line y equals x? Think about which one matches. Well, then I think it's pretty obvious to see which one it is. Obviously, it's going to be the green one. The green one is the reflection of the black one over the blue line. Okay, so we don't want this red part. Okay, and the red one was the positive square root of x. So the actual answer, when we're actually finding our inverse, it is this green one right here. Y equals the negative square root of negative x. Okay, so this is how graphing is going to come in very handy when we're trying to decipher, which of the two functions am I going to use. Okay, because when we take the square root of something and we're solving, we need plus or minus. Well, we need to decide if we have this limiting of the domain. Let's try another one here. Whoops, I got one down here. F of x equals 2x cubed plus 1. First thing we need to do is we need to replace f of x with y. Y equals 2x cubed plus 1. Go ahead and switch x and y. X equals 2y cubed plus 1. Now, if you want to go straight from the original function to this, I am okay with that. You don't need to show me bringing in y. I trust that I know what you're doing when you go from the black line to the blue line. I'm okay with that. Okay, so let's go ahead and resolve for y. So I'm going to have x minus 1 is equal to 2y cubed. Got to get rid of the minus 1 first. Now I got to get rid of the 2. So I'm going to have x minus 1 over 2 is equal to y cubed. Remember, the 2 is not part of the base. There's no parentheses around it. Okay, so if it was this, then I would get rid of the cube first. But the 2 is not part of the base, so I get rid of the 2 first. Then I got one last step. Just need to cube root both sides. Okay, so I'm going to have y equals, again, I'm just flipping it over at this point, y equals the cube root of everything on the other side. So x minus 1 all over 2. Now, when we're writing functions, I'm okay with a fraction underneath the radical. The goal here is not necessarily to simplify the expression. Sometimes this is about as good as we're going to get. Now, when we go ahead and graph this, what I hope you notice is that this function does not have a domain limiter. Okay, because when we graph this, and when we graph its inverse, what we're going to find is the inverse is also a function. Okay, so the original one looks something like this. Okay, that general shape, cubic function. Okay, you know what? I'm being lazy here. Let's not do that. Let's actually come up with some ordered pairs. 1, 2, 3, 4, and then we'll have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, I'm being lazy, so I'm going to do the black one here. If I plug in 0, what I get for a y value is 1. If I plug in 1, my y value is 3. If I plug in -1, my y value is -1. Okay, so my function, the general shape, looks something like this. Okay, now think about this. This was the point 1, 3. This was, I'm going to write this on the other side actually. This was 0, 1. And this point over here was -1, -1. Now, when we reflect, so if we have this line, y equals x coming across, and remember the line, the inverse is a reflection over the line y equals x. And we said earlier, way back when, I think I went too far actually. I've got to find it actually. It's right here. Remember, whoops, I wanted the arrow here. Remember, in inverses, the x's and y's get switched. Okay, so if I go back to the one I was on, if my original point was 1, 3, the reflection then is going to be 3, 1. That's going to be right here. And if this point right here was 0, 1, when I flip it, it's going to be 1, 0. Now, my blue line is drawn very poorly in this example, so you're not going to see the perfect reflection. What I would recommend to see the perfect reflection, use Desmos or your graphing calculator. Then you're going to see the nice picture. -1, -1, when you flip that, remains -1, -1. And then let's see if we can't sketch this. So it looks something like this. Okay, not the greatest of pictures, but I was being very lazy at the beginning, and then that's not right. Okay, if I expect you guys to be a little more exact, then I need to be a little more exact as well. Okay, so there's our picture. The original one's in black, and then the inverse is in purple. Now, we don't need to limit the function or the domain of the original one because the inverse is also a function, which kind of leads me to my last point, the horizontal line test. Okay, remember the vertical line test from pre-algebra, algebra 1, when determining if something is a function, if a graph is a function, there is a horizontal line test as well. And what the horizontal line test says, the inverse of a function is a function if and only if no horizontal line intersects the graph more than once. So if this is our original function, so let me give you an example. So we have our graph, and our original function looks like this. Okay, this is f of x. If I run a vertical line across this, or not a vertical, a horizontal line, there's no point where I'm going to cross that more than once. What this tells me is that the inverse of f of x is also a function. Okay? If my original function, f of x, the black line, does not allow a horizontal line to cross more than once, the domain is not going to be limited because the inverse is going to be a function. Now, likewise, if I have one like this, if I have a parabola or something like that, if I run a horizontal line across this one, what you can see is that I cross the parabola more than once. What this tells me here is that the inverse of f of x is not a function. Okay, the inverse here is not a function. If the inverse is not a function as the graph is originally drawn, then you're going to get some sort of regulation or limiting of the domain on the original function. So now this one you would see maybe like x is greater than or equal to 0, or x is less than or equal to 0, something like that, where you would then get the horizontal line test to work. Okay, so last couple of examples here. Determine whether the inverse of the graph of f of x is a function. Then find the inverse. Okay, so f of x equals the 2 square root of x minus 3. The picture of this, when we graph it, let me go back to the pen. The picture, when we graph this, let me draw this a little better. When we graph this, it looks something like this. I'm not real concerned about the exact ordered pairs with this one. I'm just looking at the general shape. If I look at this picture, what I see is that I could never, there's no way I could run a horizontal line across this and ever cross this more than once. Okay, so what I know now is that the inverse is going to be a function. okay, we can say that the inverse will be a function. A function. Okay? The inverse will be a function. So let's actually go ahead and find that inverse. I'm going to go ahead, I'm going to skip that line where I rewrite f of x with y. I'm going to go straight to bringing it in and switching x and y all at once. Okay? So it's going to be x equals 2 square root y minus 3. And let's go ahead and resolve for x. Okay, so we got, let's see, we got to get rid of the 2 first. So we'll have x over 2 is equal to the square root of y minus 3. Go ahead and get rid of the square root now by squaring both sides. So now when we square this fraction, we need to square both the top and the bottom. It's not going to be just x squared over 2. It's going actually to be x squared over 4. X times x, 2 times 2. Okay, and that's equal to y minus 3. We just have one more step here, and we need to add 3 to both sides. So we're going to have, I'm just going to write it over here, y is equal to, going to have x squared over 4, let's see, and then plus 3. Now, if we were to graph this function, what this would look like is something like this. And I hope you see an issue here, because this picture would match this one, but it's got this extra part right here, and that doesn't match, okay? So what we need to do, we actually need to limit or restrict the domain of our inverse, okay? We don't want this left side of the picture. We only want the right side, okay? So this right side, if we look at the x-axis, that would be 0 and everything bigger, okay? So our second part to this is we got y equals x squared over 4 plus 3, but then we're going to put in x is greater than or equal to 0, and you probably should have a semicolon there, okay? If I was doing this correctly, I should have written it all in one line. So it would be y equals x squared over 4 plus 3, semicolon, x is greater than or equal to 0. This is your official and final answer for number 1. Determine whether it's an inverse, we did that. Find the inverse, we did, but there was that extra part, this part right here, the left side, we don't want that side. So when we put in this x is greater than or equal to 0, what happens then is that this left side of the graph disappears. We're not graphing that part anymore. That's not part of our answer. Only the right-hand side, where the x's are 0 or bigger, are part of the function. Let's try another one here. Last one. Number 2. We got f of x is equal to the square root of x plus 2. Again, this one is going to definitely be a function. And you know what? Let's make it in the negative. Let's just be a little bold and daring here. So negative square root of x plus 2. So if we were to graph, what this would look like would be, let's see, x plus 2, that would be this. Wow, that's a poor drawing. That would be this, okay? That's what this picture looks like. So if we were to run a horizontal line across, we got that one there, got one there, got one there. We're good as far as the inverse being a function. So we can say the inverse is a function. Okay, the inverse is a function. So let's go ahead and find the inverse. Again, I'm going to skip that line where I replace f of x with y. Whoops. Need to scroll up. Okay, and this is as far as I can go, so we're going to be a little crunched for space. That's all right. Okay, so we're going to have x equals negative square root y plus 2. Go ahead and get rid of the negative, so we'll have negative x equals the square root of y plus 2. Go ahead and get rid of the square root. So if I square negative x, so that'd be negative x times negative x, leaves me with positive x squared. That's equal to y plus 2. Get rid of the plus 2, so we'll have y equals, let's see, that's x squared minus 2. Again, just flipping it over at that point, because most of the time functions or equations usually start with y equals. Okay, so we have our picture, and now we need to graph. Just sketch a graph here, and it looks something like that. Now the question is, which one is our final answer? I did make one small error here. I'm actually going to redraw my parabola, because the parabola, when you actually draw it, is it's down here. It looks something like this. Okay, so again, the question becomes, which one is the correct answer? Think about that reflection line. It's y equals x. Now, this is a very bad drawing, so just bear with me. If you think about the reflection, it's got to go through that line. It's pretty easy to see, I think, that the left side of our parabola is the side that matches better. Okay, they should that all 3 points should intersect somewhere. All 3 lines should intersect somewhere. So that is definitely x squared minus 2 when x is less than or equal to 0. Now, if you want to do that on Desmos, you certainly can. I will show you how in class or in person. Running out of time with this video, so I don't really have enough time to show you how in the video. You could also Google that. Just look up domain limiting or domain restrictions with Desmos, and you should be able to find out how to do that. So again, to recap, since we got this x is less than or equal to 0 in the picture, this right side of the blue is not going to be there anymore. So now, if I can try to fix this real quick, it should look something like that, graphing wise, as far as figuring out which of the two functions, the greater than 0, less than 0, which side to use.